We're starting Chapter 7 now, and in Chapter 7 we're going to look at solutions, and we're primarily interested in aqueous solutions, but we're going to look in general what is a solution. When you encounter matter, for instance, when you picked up your keys this morning, you picked up something that is a mixture of more than one substance. Your key is made of brass, and brass is a mixture that it's made by mixing copper and zinc together. Maybe you picked up a coffee mug, and your coffee mug is made of clay, and clay is a mixture of metal oxides and organic matter, and then they bake it in the oven to make it into pottery. These are all mixtures, and this is what we get in the majority of what we bump into in everyday life. Now, there's two words here that you need to understand what they mean, and that's heterogeneous and homogeneous. Heterogeneous is meaning that as you go from one place to another, that you find a different composition. And if you take your coffee mug, for example, you will see that as you go from the outside where there's a glaze, it has a different composition than the inside of the pottery, which is dull and is rather porous. That's heterogeneous, meaning as you go from one place to another in the sample that you find something different. Homogeneous means that it is the same throughout. So if you look at your key, your brass key, the brass that's on the outside is exactly the same that's on the inside. It might be a different shape, but it has the same zinc and copper composition throughout. And that's the difference between homogeneous and heterogeneous. Now, when we're looking at solutions, we're looking at a homogeneous mixture. It is so homogeneous that light moves through it as if it is the same substance throughout. And so light passes through, and we can see images on the other side. So the solution is transparent when it's a liquid. Even some solid solutions are transparent. For instance, glass is a solid solution, and it's transparent, isn't it? The reason that they are called solutions is that you have mixing of the different substances on such a small basis, at such a small level, that there is true homogeneity. So if I look at a solution of sugar in water, the sugar and the water are mixed down at the molecular level. So you can go from a sugar molecule to a water molecule to a sugar molecule, and there's not clumps of sugar and clumps of water. You see, it's mixed on a molecular basis. You can go one step higher and go to a colloid, and this is a homogeneous mixture because you have the same composition for a sample of it in one area and in another area. So milk, which is an example of a colloid, has the same composition. When it's homogenized milk, has the same composition at the bottom of the glass as at the top of the glass. However, if you get down on a molecular basis, you will find that there are clumps in there, and there are clumps of protein and clumps of fat, and then the solution surrounding it. The clumps in there, they're larger particles of molecules grouped together. They have a different composition than the solution, and so light tends to be reflected by those large clumps of particles and or the clumps of molecules, and it's usually opaque. And if you compare a solution, let's say Coke or Kool-Aid, to a colloid, an example would be either skim or whole milk, you can see through milk or Kool-Aid and see your hand on the other side. but with milk you can't. And that's because those large particles, the clumps of molecules, are interfering with light moving through the solution, or moving through the colloid, excuse me. All right, solutions now are what we're really going to focus on. They consist of two parts. There is the solute, which is present in the lesser amount, and the solvent, which is present in the larger amount. We're going to be dealing with aqueous solutions, and so water will be the solvent and will be present in the greatest quantity, so it is the solvent. Now, some solutions actually conduct electricity and some do not. Water itself, pure water, does not conduct electricity. And that often will confuse people because they're told, do not allow water to come in contact with electricity because you'll be electrocuted, and it's because water will conduct electricity. That's tap water that they're talking about, or water that you might get from a puddle or something like that. And when you have tap water or water in a puddle, you don't have absolutely pure water. There are impurities in there, and now I'm not talking about impurities that will harm you. I'm talking about something that is not water, is an impurity in water. Impurities are in water coming out of the tap, and those impurities allow water to be conductive. We call those things that when you dissolve them in water, they allow water to conduct electricity. We call those things electrolytes. There's a lot of different electrolytes. A common one is sodium chloride. The reason that sodium chloride allows water to conduct electricity is when you dissolve it in water, it dissociates into two ions, sodium ions and chloride ions. Those ions have charge and allow water to conduct electricity. Pure water has no way of taking the electrons that are in electricity and allowing them to come onto itself and then pass on to the next water molecule. But ions have charge, and they can take up and give away electrons and allow the electrons that make up electricity to pass through water. Now there are substances that you can dissolve in water that are called non-electrolytes. Non-electrolytes do not allow water to conduct electricity. Right here in this slide you can see that they're showing you hydrogen peroxide dissolved in water, and hydrogen peroxide is what is called a non-electrolyte. If I add hydrogen peroxide to water, it does not allow water to conduct electricity. There's lots of non-electrolytes that will dissolve in water. Another example is glucose or sucrose. All these things do not form ions when put in water. So there's two different types of things that will dissolve in water. There are electrolytes, and when they dissolve in water, they dissociate into ions. They break apart into ions. And then there are non-electrolytes that dissolve by a different mechanism that we're going to look at, and that's called hydrogen bonding. Now, how do we recognize electrolytes? The way that we recognize electrolytes is that we identify them by seeing, are they either acids or salts. If the compound we're looking at is either an acid or a salt, we can say it is an electrolyte. Acids have formulas that begin with hydrogen. Some examples are hydrochloric acid, sulfuric acid, acetic acid. All of those are acids and are electrolytes. How can we identify salts? Salts are metals with nonmetals. So some examples are potassium nitrate, magnesium bromide, lithium sulfate. That's pretty easy now to say, oh, that's an electrolyte. We just look to see, is it an acid, the formula begins with hydrogen, or is it a salt, a metal with a nonmetal? How do we recognize non-electrolytes? Well, non-electrolytes are compounds that will dissolve in water that are not acids and salts. So if it's not an acid or a salt, and it will dissolve in water, then it's considered to be a non-electrolyte. Now it must be able to dissolve in water to be considered a non-electrolyte. Now how do you know what will dissolve in water if it's not an acid or a salt? Those are going to be the compounds that are polar. Small molecules that are polar will dissolve in water, and carbon compounds, larger carbon compounds with no more than 3 carbons to each nitrogen or oxygen will dissolve in water. There are some with maybe 5 carbons to an oxygen or nitrogen that will dissolve, but they're not very common. 3 carbons you can count on a molecule dissolving in water. Well, let's look at an example of a small molecule that's polar. We've already looked at it, hydrogen peroxide. What about carbon compounds? These are some examples of carbon compounds that are non-electrolytes. They will dissolve in water. The first one is ethanol. Ethanol has 2 carbons for 1 oxygen, so it's quite soluble in water. If I look at glucose, the next one, it has 6 carbons to 6 oxygens. It's a 1-to-1 ratio there. Glucose is very soluble in water also. We have a principle in chemistry called like dissolves like. What this means is that polar things will dissolve polar things and nonpolar things will dissolve nonpolar things. We've already seen examples of polar dissolving polar. That's water is polar and it dissolves electrolytes, which are very polar because they're made of ions. And water is polar and it will also dissolve polar covalent molecules, which we can recognize as being carbon compounds that have no more than 3 carbons per oxygen or nitrogen. Nonpolar compounds will also dissolve in nonpolar compounds. For instance, carbon tetrachloride is nonpolar and it will dissolve octane, which is very nonpolar. Notice it's all carbon-hydrogen. And remember how we told you we consider carbon-hydrogen bonds to be nonpolar. So a molecule that's made of all carbon hydrogens is a nonpolar molecule. So how is it that electrolytes dissolve? Well, we've seen that they dissociate. They break apart into ions. We can write in a dissociation equation like we've done here for sodium chloride. Sodium chloride is a solid. You put it in water, and then it forms sodium ions, aqueous, and chloride ions, aqueous. The sodium ions dissolve because there is a negative end to water. It's polar and it has a very negative end. You see the red circles in the molecule. Those are oxygens with a del negative on them. They want to get close to that positive sodium, and so they get close and then pull it up into solution. Chlorine will dissolve in water in a similar manner, except that it has a negative charge, so the positive end, the hydrogen in the water molecule, the positive end of the water molecule crowds close to the chloride and then draws it up into water. Now that you've learned the principles of how an electrolyte will dissolve in water, what I want you to do is to draw how would water crowd around the ions in calcium hydroxide so as to make it dissolve in water. Recognize calcium hydroxide is a metal with a nonmetal, so it's an electrolyte, and it dissolves by dissociation. So write the ions that are in calcium hydroxide and then try to draw how water would orient itself around each of the ions. We start this problem by writing the ion calcium hydroxide. Next we draw the structure of water, noticing that we have dipoles in there, so I've drawn the del positives on the hydrogens and a del negative on the oxygen. By drawing the dipoles, it will help us understand how these two will orient. Calcium has a 2 positive charge, so it will be attracted to which end of the water molecule? Well, the negative end, where there's a del negative. So we bring that end close to the calcium ion. Now I drew in two other water molecules to show how the del negative in the oxygen wants to get close to the positive charge of calcium. To do the hydroxide part, we draw the hydroxide ion with its charge, and then we draw a water molecule. Notice hydroxide has a negative charge, so the positive end of water will be trying to get close to the negative charge. So we draw 3 molecules of water. I've only drawn 3. You may have drawn a different number. But notice the important point is that the positive end of water, the hydrogen, with its del positive, is trying to get close to the negative charge on the hydroxide.